Alkyl halide. Alkyl halides, we learn lots of things about dipole moments, bond strength. First of all, we will learn about the primary, secondary, tertiary type of alkyl halide. In primary alkyl halides, this is a primary. This is a secondary alkyl halide. This is a primary alkyl halides. Alkyl halides also known as haloalkane. This is introduction. Uh, the main thing I will discuss. This is a primary alkyl halide. This is attached with the 1 degree carbon. This is a primary alkyl halide. This is a primary. This is a primary. It is attached with the 1 degree carbon. This is called primary. If any alkyl halide attached with the 1 degree carbon, this is called primary alkyl halide. This is similar the case of hydrogens. 1 degree hydrogen, 2 degree, 3 degree hydrogens. This is attached with the secondary carbon. This is called secondary alkyl halide. This is a secondary alkyl halide. This is a tertiary alkyl halide. This is 3 degree carbon attached with the 3 degree carbon. This is called tertiary alkyl halide. Now we learn the name. This is a primary alkyl halide. This is a secondary alkyl halide. This is a tertiary alkyl halide. Alkyl halides are formally derived from the alkane by exchanging the hydrogens of the hydrogens for halogens, fluorine, chlorine, bromine. This is hydrogens is replaced by the fluorine, chlorine, bromine, iodine. Any one of the hydrogens, two hydrogens. By replacing these hydrogens, by putting the halogens, alkyl halide we are getting, depending on the degree of substitutions, add the carbon atoms carrying the halogens. Alkyl halide also classified as a primary, secondary, tertiary alkyl halides. This is called vinyl alkyl halide. This is vinyl. The vinyl position is the double bonds carbon position. If alkyl halide is attached, this is called vinyl alkyl halide. This is a vinyl alkyl halide. Here iodine is attached. Here iodine is attached. Here hydrogen is attached. This is called vinyl alkyl halide. This is called methyl chloride. This is called methyl chloride. Yeah, chloromethane. This is can be called as chloromethane, fluoromethane. This is IUPAC. This is a common name. This is a common name. And this is a IUPAC name. This is IUPAC name. This is called 2-iodopropane. This is a 2-iodo 1, 2, 3 positions. This is a 1, 2, 2 position, 2 bromobutanes. This is called 1, 2, 3, 2 bromo, 2 methyl propane. 2 bromo, 2 methyl propane. This is a methyl. This is a bromo, 2 bromo, 2 methyl propane. Third butyl bromide, sec butyl bromide. This name can be tertiary, secondary butyl bromide. This name need to be remembered. If there are generally not many, they are not so much important, but need to be take care that if you are learning organic chemistry, then you should know some common naming of any compound. So just remember this type of common naming, simple common naming. It is not much very important, but need to be remembered. 1 chloro 2 methyl propane, 1 iodoethyl cyclooctane, 5 chloro 2 methyl pentane. These all the things I have already explained in the IUPAC nomenclature. So if you know the IUPAC nomenclature how to write the name, then this is a simple. Only for the introduction purpose of alkyl halide, I am explaining this type of naming. The main things in this topic alkyl halide, the physical properties of alkyl halide we have to learn. The bond length we have to learn. This is also important. Dipole moments, boiling point, melting point. This is a very important. Generally two questions, average 2 questions asked, maybe sometimes 3 questions are. Yeah, one question definitely going to ask from these properties in the IIT JEE examinations. Maybe 2 questions, 3 questions. Maybe averagely we can assume 2 questions. If your time is good, then maybe 3 questions will ask in examinations. But in state level examinations, other examinations, generally 2 questions definitely will going to ask. According to the relative this concept of bond length dipole moment. So now first of all we will learn the bond length. Bond length, this is a halogen, fluorine, chlorine, bromine, iodine. This is a fluorine, chlorine, bromine, iodine. This is a fluorine, chlorine, bromine, iodine is attached as the fluorine. Fluorine is a smaller size. Fluorine, chlorine, bromine, iodine. In this order the size increases. This is a size increases. Fluorine, chlorine, bromine, iodine. Actually this order fluorine, chlorine, bromine, iodine. This is in a group. This is in a group. So in this way size increases. If you go down the group, this is a group. Size increases. If you go down the group. So bromine has a smaller size than the chlorine, bromine, and iodine. So if CH3, 3 hydrogen is attached. Here 2 hydrogens we are showing, but 1 hydrogen is in the back side 1 hydrogens. So see here fluorine is attached. So the bond length carbon and fluorine, this carbon and fluorine bond length, and this is a carbon and chlorine bond length. This is a carbon and bromine bond length. This is a carbon and iodine bond length. This bond length is higher than this. This bond length is higher than this. This bond length is higher than this. Why this bond length is higher? Suppose one atom is there. This fluorine is more electronegativity. This is electronegativity is higher. That's why dipole moment is higher. This compound's dipole moment is very much higher. So it will try to attack the electron and share per electrons. So it will make a shorter the bond length. It will make the shorter bond length. Also, the size will also matter. If the size increases, if the size, this is a smaller size, this is just bigger size, this is a little bit bigger than this and this. So if any atom is there, similar atom is there, say 4 atoms is there, carbon, suppose carbon size, if one atom is, this is a bond length. If bigger atoms will be there, then this is a greater bond length. If greater than this, then the length will be higher. As the size increases, then the length will be higher. As I have already written, the strength and length of the carbon halogens bond, CX bond, dipole moments and boiling points of alkyl halide are determined by the polarity of the bond as well as by the size of various halogen atoms. CX bond strength decreases with the increase in the size of halogens because size of p orbitals of halogens increases as well. Thus the p orbitals become more diffuse overlap with the orbitals of carbon deteriorate. As a result, CX bonds weaken and elongated. As the size increases, this is a size increases, the more number of p orbital size increases, so the distance increases. Because the bond is formed by the overlapping of orbitals, so the size of orbitals increases, p orbitals increases, so the size distance increases. So this is also one factor, and also one factor is the electronegativity. As the electronegativity increases, it will try to pull the bonds, make the shorter bond, and bond strength increases. The bond strength will be higher. This bond dissociation energy. If bond strength will be higher, then the bond dissociation energy will be also higher, because the more energy required to break a bond, because this bond is very strong. Then this bond is stronger than this bond is stronger than this. So in this way we can compare the distance and bond strength dipole moments. So the dipole moment increases, the electronegativity of fluorine, chlorine, bromine, iodine. The electronegativity increases, bond length increases. This is electronegativity fluorine is the electronegativity increases, bond length decreases. This will pull more the electron clouds towards this. That's why it decreases the bond length. This is fluorine is more electronegative, so that's why this bond length is smaller than chlorine, bromine and iodine. And bond strength, fluorine CF bond strength will be higher than chlorine, then the bromine, then the iodine. In this way the bond strength order will be there. Why bond strength? There more electronegativity, it will try to pull more electron towards this, bond becomes shorter and more strength. That's why this is a strength increases in this order. And the molecular size, as you go down the group size increases. This thing all you know, that in the periodic table you have learned that as you go down the group, size increases. So iodine will be greater size than the bromine, then the chlorine, then the fluorine. The dipole moment, the term dipole moment can be defined either with respect to the chemical bonds or with respect to the molecule. This is dipole moments, bond dipole moments and molecular dipole moments. We will learn two types of dipole moments, one bond dipole moments and second is molecular dipole moments. This is a bond dipole moments. Something in introduction we will learn. The electron covalent bonds connecting two different atoms are not equally shared by the atoms due to electronegativity difference between the two atoms. Suppose these two atoms are taken, A and B. Suppose B is more electronegativity than A. Suppose B is more electronegativity than A. Then this will be the bond between A and B is in this way. It will try to pull more electrons towards it. If it will be more electronegativity, it will try to electrons, this share pair electrons. This is a share pair electrons. This is electron clouds. It will pull more and more electrons towards it. If B is more electronegativity than A. If A will be more electronegativity, then it will try to pull more electrons towards this. So if there is electronegativity difference will be there, then the share pair electrons will shift more towards the more electronegative atoms, and electronegative atoms will develop a partial negative charge because it has more electrons, and it will electron deficient. It will like electron deficient, it will lose electrons. So that's why this is partial positive charge will be developed, and the distance between this is d. It is not denoted, it is not necessary, but this way. And the dipole moments, if chlorine is more electronegative than the hydrogen, so dipole moment will be indicated like this bond. This is a arrow, and this is a one sign is there, it is like plus sign, it is an arrow. If this sign will be in which side, this sign will be negative side, this sign will be in the positive side, this sign will be in the positive side. Actually del minus is shown in this side, but actually del minus, here del minus. In this way the del minus del plus sign is shown. This chlorine will be get partial negative charge because it has a greater electronegativity than the hydrogen, so the dipole moment will be shown in this way. The arrow will be in the electronegative, more electronegative atom side, and plus this plus sign will be in the tail will, this is a cross, in tail will be in the less electronegative atom sides. So the atoms of more electronegative atoms has greater share of electrons than the atoms less electronegative elements. Consequently, the atoms that has a greater share of bonding electrons bear a partial negative charge, and the atoms has a lesser share of partial positive charge of the equal magnitude. The partial positive and partial negative charge is equal in magnitude. Actually, del plus is equal in magnitude. For the magnitude is shown, and del minus, it is equal in magnitude. For the magnitude plus minus it is not considered. Then del, whatever the charges will be, if it will be 2 coulomb, then it will be 2 coulomb, it will be minus 2 coulomb, it will be plus 2 coulomb, but the 2 coulomb will be, the magnitude will be equal. In this way I want to make clear. Here AB is taken. AB is not any atom, but for the general to understand for in a general manner, so I have taken A and B. But this example you can consider the similar example. Chlorine is more electronegative than the hydrogens. That's why this chlorine is getting partial negative charge. This is partial positive charge. Dipole moment has a magnitude and a directions. This need to be take care. A dipole moment is a vector quantity. If you in physics you will going to learn dipole moment is a vector quantity because it has both magnitude and direction. If any quantity has both magnitude and direction, that it will be vector quantity, not a scalar quantity. If any quantity has only magnitude, then that will be a scalar quantity. So what is the standard definition of dipole moment? The mathematical product of a magnitude of charge either on atom A or on atom B, and AB bond separation length D is called dipole moments. Dipole moments means either charge on A and B. If either charge on A and B, charge into distance between the two atoms, it is a distance between the two atoms, and charge on the either atoms, it is a product of the charge on either atoms and distance between the two atoms. It is dipole moments has a dB, it is a unit of dipole moment. This is a dipole moment, this is a mu. This in this way dipole moment can be denoted like of AB atoms. Here dipole moments of HCl equal to del into D. Del, I am not saying del minus del plus, I am saying only del. Del means only charge, not negative charge, not positive charge. I am not considering here negative positive, I am only considering their magnitude. So dipole moment, the definition need to be remembered. If any theoretical example definition is necessary, the sign note need to be remembered. dB is the sign note units, D is the distance between them. Suppose these two compound is there, here CX compound is there, and if other CX compound is there, here this is one similar thing I am writing. If this is a more electronegative, then this will require a negative charge, this will require a positive charge. This will be more electronic, this will require a negative charge, this will require a positive charge. As this negative charge positive charge will be there, then there is a attraction between this negative positive charge will be there. This is attractions like if 2 plus charge and minus q charge is there, there is attraction between a positive charge. So this is attractions. In electrostatics, in physics, in electrostatics chapters, we have learned that there is attraction between the unlike charges, there is a repulsion between the like charges. If plus q and plus k will be there, then there will be repulsions. If the attraction will be there, then this way there is a attraction, unlike charges will be there. So in the similar manner, there is attraction between the opposite charges. So there is a, this is a, I am explaining why I am explaining this thing, because the application of this thing we will learn in these topics. That's why I am explaining little things, so that you can get much clear in letters. Molecular dipole moments. Any compounds, suppose water molecule. This is a water molecule, so there is a dipole moment. So overall this is a dipole moments, here dipole moments, here dipole moments. So overall dipole moments in this direction. So the any atom, suppose SCl has a dipole moments, is a bond dipole moments, but if any molecules with more than 2 3 4 5 atoms is there, then there should be also a dipole moments. With dipole moments and the molecular dipole moment is a vector sum of all the dipole moments. By the definition, molecular is electrically neutral. By the definition, molecules are electrically neutrals. What about the plus minus? That's why there is a molecule. If molecule will form, then there is that will be neutral. Why neutral? If the molecule not be neutral, then how can the molecule will form? If any molecule is there, then that should be a neutral. A molecule has a region, a pole bearing a net positive charge and opposite region. The molecule has a region, has a partially positive charge, partially negative charge, bear a net partially negative charge of equal magnitude. There is equal in magnitude. Del and del. Del means here is del, here is del. Means del. If here 2 are 2, what will we say? If plus 2 and minus 2 will be given, then this will be equal in magnitude but opposite in charge. If x is x plus x and minus x will be there, then this will be equal in magnitude but opposite in charge. Similarly, del is there. Here x is the same. If x and plus x is there, minus y is there, then we can say that they are not equal in magnitude, and not they are opposite in charge. But here is x and x means both equal in magnitude. That's why the plus tail minus tail, del is given, and this means equal in magnitude but opposite in charge. If I will explain later. Bear a net partial negative charge of equal magnitude and is shown in the systematically below. Such molecule has a dipole moment which is equal to the vector sum of dipole moment of all the bonds in a molecule. If any molecule is given, then we have to find the vector sum of all the dipole moment of a bond, and the dipole moment is a vector quantity. Then we have to find the vector sum including all the directions, magnitude. That will be the molecular dipole moment. Dipole moment of a molecule being a vector has a direction which is shown using the following symbol. This is a, in this direction will be in the del minus, this direction will be del plus. This is a plus, so for remembering purpose, here is a plus sign, is similarly plus sign is there, so it will be plus, here will be the minus sign. If any HCl is there, this is a minus, this is a plus, so we have to sign so in this way. This is a minus, that's why this is a plus. So this is a direction of dipole moment. This means that the overall dipole moments is in this directions. Overall dipole moment is in this direction. The arrowhead of the symbol is pointing towards the negative pole and plus sign towards the positive pole. This is plus sign, tail sign is towards the positive poles, and arrowhead sign towards the negative pole. A molecule not have the dipole moments despite containing bonded to. Means a compound, this compound doesn't having dipole moments, but it is having a bond dipole moment. This bond has a dipole moment, this bond has a dipole moment, but this bond has a dipole moment in this direction, this bond has a dipole moment in this direction. It is shown in this manner. This dipole moment has a dipole in this direction, this bond has a dipole moment in this direction. So overall, this direction, this direction, dipole moments are equal in magnitude but opposite in sign. This is a dipole moment. This is a, suppose this is a plus dipole moment and this is a minus dipole moment. So this plus minus become a 0. So the overall dipole moment is 0, but having bond dipole moments, but the overall molecule dipole moment is 0. This is why we are 0. We are at addition. We are doing addition in vector addition. So in vector addition, sign, magnitude both should be added. But in the scalar addition, we have to add magnitude. But we are not a scalar addition. We are not doing a scalar addition. We are doing vector addition because dipole moment is a vector quantity. So we have to add both magnitude and direction. So that's why we are getting 0 dipole moments. Some important point is there you need to be remembered. Both dipole moments can be determined experimentally. Only molecular dipole moments can. Bond dipole moment can be determined experimentally. Only molecular dipole moments can. However, there is an indirect way to determine the bond dipole moments approximately, if the not accurately. We determine the approximate dipole moments, not the accurate dipole moments. And however, diatomic molecules has only one bond. Therefore, dipole moments of the bond in a diatomic molecule is equal to the dipole moment of the molecule. Means in a diatomic molecules, suppose in diatomic molecule has a dipole moments or bond dipole moments. Diatomic molecule, two atoms there, A and B. So this is a bond dipole moment. This is a bond dipole moments. Only one bond is there. So this can be also called as a molecular dipole moments, because this is a only one bonds. If any compound has a 1, 2, 3 bonds, then we can add vector addition and can get a molecular dipole moments. But this compound has only one bonds, so this is can also be called as bond dipole moments is equal to the molecular dipole moments. For example, experimental dipole moments of HF is 1.91, and thus the dipole moments of HF is 1.91. In some organic molecule, one bonds contribute overwhelmingly. Suppose this is a molecule. In this molecule, this Cl bond, the bond dipole moment is very much higher than CH. CH approximately 0 volt dipole moments. CH there is approximately 0 dipole moments. One bonds contribute overwhelmingly to the dipole moments, making the contribution of the other bonds insignificant. This is a little bit dipole moments. It is very less as compared to the Cl dipole moments. So the molecular dipole moments, whatever the molecular dipole moments, will be equal to the Cl dipole moments. So the Cl dipole moments is very much higher, so it will dominate than the other dipole moments. So this only one single bonds will be represent the molecular dipole moments than the whole dipole moments. So this dipole moments will be considered for the whole molecular dipole moments. So the bond dipole moments equal to the molecular dipole moments in such case where this will be very much higher. If any bonds has a very much higher dipole moments, then that will dominate the other dipole moments are over mainly to the molecular dipole moments, and this will be the our dipole moments. Now the electronegativity difference between C and Cl is much higher than the CH. C and H. Bond length of Cl is much higher than the CH. Thus the dipole moment of Cl is much higher than the CH. Thus the dipole moment of Cl is approximately same as the dipole moment of CH3Cl. In this example, the dipole moment of CH3Cl will be much higher. Experimentally, the dipole moment of CH3L is 1.87, meaning the dipole moments of the CCl bond is in CH3Cl is approximately 1.87. Experimentally, the dipole moments of this compound is this much. That's why the dipole moments of CCl in CH3Cl is 1.87. As this molecule dipole moment is this compound's dipole moment is molecular dipole moment is considered as this bond dipole moments. That's why if experimentally we are getting the CH3Cl dipole moment is 1.87, then the CCl dipole moments will be 1.87. The molecular dipole moments can provide useful information regarding the structure of the molecule. This is a very important. Molecular dipole moments provide the useful information regarding the structure of the molecules. This is suppose H2O. This H2O it cannot be like in this format. H2O will not like in this format. If experimentally we are getting the bond dipole moments, experimentally we are getting the dipole moments of the water molecule is 1.85. If we are getting 1.85 dipole moments, implying that the water molecule is not linear. So in this linear structure will be there, then there should be in this dipole moments. So the dipole moments will be 0 if this structure will be there. But experimentally we are getting dipole moments of water molecule is 1.85 dB. That means the structures will be somewhat different from the linear structure. So what is the actual structure? Dipole moment is a vector quantity and dipole moments is a vector sum of individual bond dipole moments. It represented by a small arrow with the tail in the positive center and head pointing towards the negative center. So the water molecules will be H and H. The actual structure of water molecule will be in this way. So this way, there is a dipole moments in this direction. Oxygen is more electronegativity. So the overall dipole moments will be in this direction. So overall dipole moments will be in this direction. That's why we are getting 1.87 dB dipole moments. So the structures, dipole moments also give the information about the structure of the molecule. So dipole moments. Here is the row. I will make here this compound dipole moments for the order is something different. For if you first time see if any student then thinking that dipole moments should be if any student first time see this compound then thinking that dipole moments should be in this order, should be in the order. if first time any student see, then thinking that this should be the order of dipole moment, because this is a higher electronegativity than this. As the electronegativity increases, dipole moment increases, but something change in this compound. Dipole moment of this will be higher than this, so the order will be different. Chlorine, fluorine, bromine, iodine. Only this will go first, and this will become second. This will become first. It will become second. This will become third and fourth. In the dipole moment will be there. Why the orders are changing in this compound? The order is changing because dipole moments mu is equal to del into distance. Del is a charge. The charge, how much will be charge develop? Each charge will be develop depending upon the electronegative difference between the atoms. Whatever the atoms are attached, there is a difference between the electronegative. Is result by the result of the difference in electronegative, this partial charge will be developed. And the distance, this is a product of distance. One thing is right, this is fluorine is more negative, electronegativity, it develops more and more partial negative charge, positive charge, any one charge, it will develop more charge. But it is also, in deciding the dipole moment, you have to also consider the length. So the chlorine is just fluorine is a higher electronegative, so the size is very smaller, but the chlorine size is very much higher. Suppose fluorine, if you fluorine, chlorine and bromine and iodine, the difference between this size will be not much higher. The difference between this not much higher, but this difference between fluorine chlorine is very much higher. The size is very much higher. So the dipole moment of chlorine is exceptionally methyl chloride. This methyl chloride, this is called methyl chloride, exceptionally much higher than the methyl fluoride. The methyl chloride is exceptionally the higher dipole moment than the fluoride, methyl fluoride. So we have to need to take care the dipole moment of this compound. So that why these are different, so I have explained. This is a product of del and distance. So the distance, because of the distance factor, as the size of chlorine is very much higher, that's why the methyl chloride has higher dipole moment than the methyl fluoride. So this thing need to be remember. But the dipole moment of fluorine, chlorine, bromine, iodine, dipole moment actually check between the atoms, but fluorine, chlorine, bromine, iodine higher electronegativity. So the dipole moment of fluorine, chlorine, bromine, iodine here is higher. But when the methyl will come, the dipole moments of methyl chloride will be higher than the fluoride, bromide and iodine. Whenever this chloride will come, this methyl, whenever the methyl will come, so need to be take care. When this fluorine will be attached, only methyl, when the fluorine will be attached, 2 fluorine, 1 fluorine, 3 fluorine, 4 fluorine. So according to the some constant of dipole moments, del into distance, all the factors are decided in experimentally. The dipole moments come in this order. There is a chloride, this need to be take care. This compound chloride will be higher than the bromide. I have 2 fluorine is higher than the 1 fluorine, 3 fluorine, 4 fluorine, 1 2 3 4, this should be order. But according to the experiment, the del into distance, so the factor will, these two factor will give the dipole moment. So according to this, the dipole moment of 2 fluorine will be higher than the 1 fluorine, than the 3 fluorine chlorine. So need to be also take care. Here is chlorine is higher dipole moment than the water molecule, this the fluorine, then the NH4. This also need to be take care the dipole moments in deciding the, because in the examination there will be some question regarding this concept. Have to compare the dipole moments, which one is higher dipole moments. So this need to be remember the order. This is a chlorine is a higher dipole moments. Why? This is a very higher size. Chlorine has a very much higher size. That's why this is higher dipole moments. This is a water molecule. This water molecule has a hydrogen bonding. That's why this should be higher dipole moments. Here I have written CH3Cl is having greater dipole moment due to the greater size of chlorine, and H2 has a hydrogen bonding. And last two is taken as electron difference with the consideration. This is HF is higher electron difference in the nitrogen and then hydrogens. That's why this is HF is higher dipole moment than this. But this is hydrogen bonding. This H2 is forming hydrogen bonding in the water. That's why this is higher dipole moments. And chlorine has a higher electron. Chlorine is higher size. That's why this is a higher dipole moment. So this type of order we need to be remember. In examination we may confuse if you don't know the order. What is the order? So this order need to be remember. Here is also fluorine. When fluorine is attached, 2 fluorine is higher dipole moment than the 1, then 3 and 4. 4 fluorine will be attached. Here the 4 fluorine will be attached. Then the dipole moments will be, here dipole moments will be cancel each other. So dipole moment will come 0. But this order need to be remembered. Here chlorine, 1 chlorine is higher dipole moment in the 2 chlorine, 3 chlorine, 4 chlorine, 0. Bromine 3 is higher, 1 is higher, 2 is second higher, 3 is third higher, 4th is 0. Iodine, this one iodine is higher than the second and third, but in the fluorine the order will be different. So in the this thing also need to be remembered. When fluorine is attached, this will be second, first, 3, 4. This thing I have already explained. When the fluorine is attached, second will be higher than the one, third, fourth. So the order, this type of things need to be remembered in the examinations, because in the JEE advanced, JEE main advanced, they will make confused by this type of questions. So need to be remembered. Dipole moments depend on the three factors: polarity, magnitude, and geometry. So in the homonuclear diatom molecule have a zero dipole moments due to absence of charge. This is a homonuclear diatom molecules. This is a zero dipole moments. There is no any difference between these two oxygen. That much how much the this oxygen is electronegative, that much is this. So the del, the electronegative difference is 0, so that partial charge will not develop. So the mu is del into distance. So del is 0 into d. So the dipole moment will be 0. So the homonuclear diatomic molecule, the dipole moments will be 0, but the diatomics molecule of different atoms, this is hetero diatomic molecule. So this is a different atoms is there. So the fluorine is high electronegativity, so it will develop a charge, and also there is a distance, so it will develop a dipole moment. This dipole moment is equal to 1.9 dB. And this is a chlorine is also, there is a difference between electronegativity between the hydrogen and chlorine, so there is a development of dipole moments. Polarity molecules, this is a polarity molecules, this is a structure is there. So this is in this way the dipole moments will be 0, because they are cancelling the dipole moments, because this is a molecular dipole moment, so you have to find. And this molecular dipole moment, this is having dipole moment, this is having dipole moment, but it is in opposite sides. This bond having dipole moments, this bond having dipole moments, but they are overall the dipole moments of the molecule will be 0, because dipole moments is a vector quantity, so we have to add vectorally with sign directions and with the magnitude, so the dipole moments will be 0. Molecule having angular or bent structure have a certain value of dipole moment. This is having certain value of dipole moments. S2 has a 1.84 and S3 has 1.43. The molecule is a polyatomic molecule is symmetrical, then the dipole moments will be 0. This is a symmetry molecule, CCl. Symmetry molecule CH. If in this way there is a symmetry molecule, so the dipole moments will be 0. So such type of symmetry molecules dipole moments will be 0. This need to be take care. Importance of dipole moments. The measurement of dipole moments helps in deciding and distinguishing between the polar and non-polar molecules. If the non-polar molecule will be there, then dipole moments will be something will be there. If non-polar molecule will be there, then dipole moments will be 0. If the polar molecule will be there, then dipole moments should be there. Non-polar molecule have a 0 dipole moments, while polar molecule have some value of dipole moments. Non-polar molecules such as O2, Cl2, BF3, CH4. This is a non-polar. This is a symmetry. So that's why there is a non-polar. Polar molecule HF, HCl, H2S. This is a polar molecule, so this is having dipole moments. Dipole moments measure the. Now it is clear non-polar molecule has a dipole moments, and non-polar molecule has 0 dipole moments, and polar molecule has a dipole moments. Dipole moments may give us about the degree of polarity in the diatomic molecule. The greater is the dipole moments, the greater is the polarity in the molecule. This need to be take care. Dipole moment is to find the shape of a molecule. This is because the dipole moment not only depends on the individual dipole moments of a bond, but also the arrangement of the bond. So this thing also need to remember. This is also very important. Shape of the molecule. As the H2 molecule has a 1.8 dB something dipole moment. So the H2 molecule is in this way bent structure. So means if you are given H2 molecule in this format, then you can say that this is a wrong structure. Why this is a wrong structure? Because H2 has 1.8 dipole moment. So if this structure will be there, then dipole moments will be 0. Dipole moments will be 0, but this structure is not actual structures, because there is a dipole moments in the water molecule. So in this way we can get to know about the structure of the molecules and shape of the molecule by the dipole moments. If the dipole moments will be 0 means the molecule will be non-polar. If the dipole moments will be 0, then there is a possibility that the molecule will be symmetry. So in this way we can get to know about something shape of the molecules. degree of polarity, how much that polar is the molecule by dipole moments. If dipole moments increases, polarity increases, so the bond length decreases. In this way we can get to know something about the dipole moments. Dipole moments also also related to the boiling points. Also dipole moments is a very vast uh, knowledge, is very fast, very, there is very lots of things need to be learned about dipole moments. There is lots of application dipole moments, so we will learn it one by one the applications. But here we have learned the basic what is required to know the dipole moments. Now we learn all the application dipole moments in the boiling points. Everywhere there is application dipole moments, there is bond length, boiling point, multi point, strength, anywhere. So now we learn about the boiling point.